All right, so this video deals with surface water, in particular flooding. Would coincide with the Roland Park field trip that we're not going to be able to do, um, and also the lab in the investigation manual, pages 30 to 33. All right, so really what we're going to be doing is determining the likelihood of a flood in a given area along a stream. Um, And so one of the things that I would say about streams and water, and I've said this before in class, is that um, they are short-term investments, not long-term investments. And so here today we'll be able to calculate the likelihood of a home or business near a stream being flooded, what the recurrence interval is. In other words, what is the expected time period between floodings, and what would be the magnitude of the flood. To do that, we first will calculate stream discharge. And this is really the first part of the lab. So thinking about that, how would we be able to determine the discharge or the amount of water that is flowing in a stream, and what would the units be? Give you a moment to think about that. All right, so we would need to know two things, right? We need the area of the stream, how much space is being taken up by the stream, and the speed of the water, or the velocity of the water in the stream. And so you can see that here in this diagram. We have the water moving at 1 meter per second. We have the width of the stream at 10 meters and the depth at 3 meters. Now that's great, but streams are not perfect rectangles. And in fact, the water is not moving at the same velocity everywhere in the stream. So this poses some challenges. And that's really what the first part of the lab is getting at. But to look at a second example, here we have the speed, the velocity at 2 meters per second. We have the width at 10 meters and the depth at 9 meters. So that gives us everything we need to calculate discharge, which you can write it out two ways, right? It could be that discharge equals the cross-sectional area times velocity, or what that actually means in the case of the example on the right is 10 times 9 times 2. All right, and you can see that that gives us meters 1, 2, 3 times, so cubic meters per second. All right, so discharge is the amount of water that's passing through a given spot in the stream per second. Okay, the amount of water that flows past in 1 second. All right, so there's our equations there. Again, we can write that a few different ways. And this is really the first part of the lab, the first 5 questions in the table. But what it's really getting at is the fact that streams are irregular shaped. And so here we have a stream that's 14 feet across by 4.3 feet deep. But you can see that that's not true. It's not a perfect square. Or I'm sorry, not a rectangle. All right, so that would be, if we did that, that would be an overestimate, right? We would not be accounting for the fact that there is not water in these two light blue areas here. All right, so we may be tempted to do some other geometric shapes. I'm sure you've taken some geometry where you've taken a irregular object and tried to make it into geometric shapes and use math to do that. But in this case, if we did something like this, this would give us an underestimate. All right, so the lab that we do out at Roland Park is that we enter into the stream with waders, and we section the stream off into segments. So here you can see 7 segments. The stream is, in this case, 14 feet across. So each segment has a width of 2, and you see that down here. That's consistent for all of this. But the depth varies as we go across to the center of the channel. 4 is our deepest, and you can see that here in the table below. All right, and then we can calculate the area for each of these 7 segments, which is what you see here on the right, and then add all those up, and we get this cross-sectional area. So that's really what questions 1 through 5 in the lab on page 30 and 31 in the investigation manual do, is just have you look at these overestimates and underestimates. And really it's to practice calculating discharge. So that is something that I want you to be able to calculate, is discharge. Now, I also said that that's affected by the fact that the velocity is not the same throughout the stream. And so this question is asking where the stream water would be moving the fastest. So here we want to think about the friction of the water along the channel of the stream and where it would be slowing down. So if we look at something like this, a little hard to see here, we have this zone here in the center of the stream, not all the way to the bottom, that the stream is moving faster. Again, the arrows here, the larger the arrow, the faster the water is moving. We see that there's some friction along the side of the stream, and so the water is slowing down, and also here at the bottom of the stream. All right, so that leads us to how we would want to calculate this, and this is shown again in the table 1 on page 31, that we want to measure about 60% of the way down into the stream from the surface level. All right, so this would be a good time to pause and just complete questions 1 through 5 and table 1 again on page 31. Okay, so after you've calculated discharge and have a good understanding of what discharge is and how we could calculate it, we're going to move on to look at flooding. And for those of you that have been in the area for a while, you remember the Ellicott City floods. There were 2 that happened about 2 years apart. You can see the dates here on the screen. Both of these were listed as a 1,000-year flood, which is one of those terms that throw people off. How can a 1,000-year flood happen, not 1,000 years apart, but 2 years apart? And so we want to try to be able to answer that. I'm sure you already have a sense of statistics and probability, but we want to apply those to floods. All right, so telling you something you probably already know, but 90% of all U.S. natural disasters declared by presidents have involved some sort of flooding. So hurricanes, from just flash floodings and things of that nature, tornadoes. And then an estimate of sort of the cost associated with some of these things. You can see here this example from Cedar Rapids, the cost associated quite a few years ago. So expect a higher cost today's money. All right, so I think you know what a flood is, although the term can be a little bit tricky, right? Because as the water moves out of the channel onto the flood plain, you can see that that flood plain actually extends further and further, right? So how high the water is or how far it is onto the floodplain give you these different kinds of floods, right? A 10-year flood or a 20-year flood, and so on and so forth. All right, and so we spend a lot of time, energy, and money creating ways to prevent flooding from occurring. Here you see a levee that has been breached as the water has come through it. And so we try to build these, but streams naturally build up these levees as well. And you can see this in this series of diagrams that we have the channel and the floodplain. And over time, sediments build up these sort of natural levees along the channel. As water overflows the channel, it deposits more sediment, and that natural levee builds up over time. All right. So, one of the things that we see when we go to a place like Roland Park is as you're walking along the side of the stream, you can definitely see evidence that the stream has overflowed its banks at some point in the past. And unfortunately, one of the easiest ways to have students look for this is, trash. Seeing where the trash has been deposited on the side of the stream, sometimes wedged into tree trunks or overlying branches. You can get a sense of how high the water was by the debris that's stuck there. You can also see that sort of washed out onto the path sometimes. All right, so that kind of brings us to part two. I'm not going to have you do part two yet. I'm going to walk through this process. There is really just a series of graphs that we have in the lab investigation manual. But first, let's start with the Roland Park field trip. So this is what we are able to do, and probably something that you could have your students do, is to calculate really the discharge of the stream. You need a tape measure. You can see that these folks are wearing waders because we are in some water that we're not real sure of the health of the water, so we want to be precautious there. And then this person here just has an instrument that can measure the stream velocity. So those are a little pricey, but it might be possible to work with another agency to get one of those. So what they're going to do is just what we've seen in the previous graph of the stream. They're going to measure the total distance of the stream, the width, and then they're going to break it into segments, and then they're going to use this sensor to measure 6/10 of the way down after they measure the depth of the midpoint of each of those segments that they've made. They're going to measure down and record the velocity. So they'll have the width of each segment, the depth of each segment, and the velocity 6/10 of the way down. All right, so here's an up-close picture of what that looks like. Here's the tape measure. Here's the sensor. All right, and then what we end up doing is drawing something that would look a little bit like this. You can see the scale here for horizontal scale going across each of these segments. Their little red spot here in the center measures the midpoint between each segment, and so that's what we have here. That's where the measurement was taken. And the vertical scale has the depth of each of those. So we could use all of that then to calculate very accurately the discharge for the stream. All right, and so the discharge of the stream, the amount of water that's passing through, is related to the stage height, the height of the stream, right? How high the water is. Obviously, if there's more water passing through a given stream, something that you may have been able to walk through with those waders on, one day when the discharge is higher, the water might come into your waders, right? The water height is going to be higher, and that's what we mean by stage feet here. All right, so obviously this varies with precipitation and runoff versus infiltration. So something about the water cycle again, whether the water is slowly percolating into the ground or running off because of impervious surfaces, blacktop concrete, things of that nature, parking lots. And then the amount of precipitation and the sheer volume of water. All right, I'm going to skip that for now. So this obviously varies over the course of a year, and here we just have an example of that for a river in Idaho, where we see that a lot of the snow melt is causing the discharge to increase, and these periods where it spikes and then decreases. So these would be probably related to temperature changes, for example, in this case of snow melt. And we can see that the discharge is not static. It changes over time, right? It's going to change with weather. All right, so I'm going to just talk about weather, and then we'll stop here and pick up in part two. So one of the things that we could think about is what's happening weather-wise in an area. And so what we want to focus here is the blue line, which is precipitation. And you can see for the period that I have here, April 19th to April 24th, the most precipitation we had is on April 24th. So think about what that week would look like in terms of stream discharge or stream gauge height. I'm going to pause here and we'll pick up and look at those graphs in the second part.